Hello and welcome to the second video of the FP1 chapter Proof. Quick question on the screen to review the previous video. Write down the 4 steps of proof by induction. I had these color coordinated, I'm going to stick with that. So the first one is the basis step. And that was doing it when n equals 1. The second step we had was the assumption step. That was assuming your statement was true when n is equal to k. And we assumed that for the inductive step, where we needed to prove that if it is true when n equals k, then it is also true when n equals k plus 1. Finally, the inductive step, together with the basis step, gave us the conclusion step, which was just to say that if this is true and this is true, then it is true for all natural numbers or positive integers. In this video, we're going to use the same idea, proof by induction. We're going to look at divisibility results, and there's a slightly different approach to doing this proof for these types of results. Jumping straight in with an example, proof by induction that for all positive integers n, 3 to the 2n plus 11 is divisible by 4. One way you could do this is just to start playing with the expression, throw in k plus 1, and try and show it's divisible by 4. But what I want to do is to show you a process that you can do more or less the same thing every time you've got a divisibility proof. So what I'm going to do is say let the function of n be equal to 3 to the 2n plus 11. So we're making this our function. Then, when n is equal to 1, we can do the basis step. And we can say 3 to the 2n, which is just 2, plus 11 is equal to 9 plus 11, 20. And to show that's divisible by 4, I'll pull a factor of 4 out the front, and obviously there's a 5 left over. So this is the function when n is equal to 1. For the assumption step, now I can replace the n with a k and write f of k. And that will be 3 to the 2k plus 11. And our assumption here is not that, that's not the assumption. The assumption is that this is divisible by 4. So what I'm going to write is this is equal to 4, and then you can choose another dummy variable, let's say q, where q must be an integer. So if you can write this as 4 times an integer, that means that this number is divisible by 4. And probably it's all going to be positive because we're talking about positive integers in here. So my assumption here is this little bit here, divisible by 4. Now my induction is to say what happens when I use k plus 1. And that gives me 3 to the 2 times k plus 1 plus 11. And I need to prove that this is divisible by 4. And as with the previous one, this is where the bulk of your work will go. Because you can't just write equals 4q like I've done here. This was an assumption. We need to prove that this is true, if this is true. To do this, there's a fairly standard approach that is not intuitive at all. We can subtract f of k, and we can't do that by itself. You can't just subtract f of k randomly. That completely changes it. But you can do that if you also add f of k, because of course those two will cancel and give you 0. So I haven't changed the overall expression, but this is a very useful thing to do, because this and this together we can manipulate. And if we can manipulate to show that this is divisible by 4, we've assumed that this is divisible by 4, and that will form part of our if statement. If this is divisible by 4, which we've assumed it is, then all of this will be divisible by 4, assuming of course that we can make this divisible by 4. So let's have a look at that. This is a good process because often this will help you bring in some extra elements that manipulate together with these to give you what you want. So we've got here 3 to the 2k plus 2 plus 11 minus the function evaluated with k, so that's 3 to the 2k plus 11, and I'm just going to leave that as the function of k, because that part at the end will just say, assuming this is divisible by 4. So I'll leave that there, and these other things can interact. So index rules coming into play here, 3 to the 2k plus 2, I can separate that plus 2 there and make this 3 squared times 3 to the 2k. So that becomes 9 times 3 to the 2k plus 11. Open up these brackets, minus 3 to the 2k minus 11 plus f of k. Now the plus 11 minus 11 cancels, and here is a really useful thing. This is why it's useful to do this, to get these interacting. We've got 9 lots of 3 to the 2k minus 1 lot of 3 to the 2k. That gives me 8 lots of 3 to the 2k. And I've still got plus f of k here. Now 8, of course, is divisible by 4. And we're assuming that f of k is divisible by 4. And if this is divisible by 4, then this whole thing is divisible by 4. So now we've got our final statement. We have proven that if this is divisible by 4, then this is divisible by 4. And then we come to our conclusion step. As usual, we know that this is true. And we have proven that if it's true for n equals 1, it must be true for n equals 2. And if it's true for n equals 2, it must be true for n equals 3, and so on and so on. So these two together gives us our statement, true for all natural numbers. And there we go. There are other ways to do this. You don't have to start with this, but I think this is a really good way of doing it because it gives you a standard starting point for any proof for divisibility rules. So although I think my writing's over the top of it, let me clear that off. For divisibility rules, my suggestion would be try starting with this for your proof, your inductive step. And generally, that's a good way to start. It will give you some terms to play around with and combine to give what you need. And that's how I'm going to do it for the next two examples. So let's start that again. We've got here a new function, and that is n cubed minus 7n plus 9. So my basis step, when n is equal to 1, I've got f of 1 is equal to 1 cubed minus 7 times 1 plus 9, and that gives me a 3. And of course, 3 is divisible by 3. Now my assumption that f of k is equal to 3q, where q is an integer. So I'm assuming that the function evaluated at k is divisible by 3. That's what that means. And that f of k, of course, if you want to write it out, is k cubed minus 7k plus 9. Now for my inductive step, I need to prove that f of k plus 1 is also divisible by 3 if f of k is divisible by 3. And as I said, I'm going to take that and then subtract f of k and add f of k. So I haven't changed anything, but it gives me a few terms from f of k to bring in and interact with these. So that gives me k cubed plus 3k squared plus 3k plus 1 minus 7k minus 7 plus 9 minus f of k, which is k cubed, and then minus 7 gives us a plus 7 there, and minus 9, and on the end plus f of k. So I've just expanded all of this out and substituted in this with a negative in front. Combine what I can, cancel what I can. I can cancel the k cubes, that's good, I don't want those. Then I've got 3k squared and plus 3k. Oh, there's more I can cancel. Oh, there's more than that. Of course, I can cancel those as well. So I've got plus 3k plus 1 minus 7 is minus 6 plus f of k, and this is nice because all of these are divisible by 3. And of course we know that k is a positive integer because that's all we're talking about, positive integers. So this thing in brackets is obviously a positive integer. So this is divisible by 3 because I pulled a factor of 3 out the front. And assuming f of k is divisible by 3, then f of k plus 1 is also divisible by 3. True for n equals k plus 1. If it's true for n equals k. And that, together with our basis step, knowing it's true for n equals 1, tells us it must be true for all natural numbers. Final example. Prove by induction that for all positive integers n, 11 to the n plus 1 plus 12 to the 2n minus 1 is divisible by 133. Okay, on the face of it, this one looks a little bit nastier, but it's pretty much the same idea. Make it into a function of n. We've got 11 n plus 1 plus 12 2n minus 1. The basis step when n equals 1. That's 11 squared plus 12. 2 times 1 minus 1 is just to the 1. And obviously 133 is divisible by 133. So it is true for n equals 1. Great. Now we're going to assume when n is equal to k that this thing is divisible by 133. Using that, my inductive step, f of k plus 1, we've got 11 to the power of k plus 1 plus 1 plus 12 to the power of 2 times k plus 1 minus 1 minus f of k plus f of k. So I'm going to simplify this a little bit here. We've got k plus 1 plus 1, so that's k plus 2. And I want n plus 1. That's a useful thing for me to keep here, because it's part of the function. So I'm going to separate off the plus 1 on the outside as an 11 times this, but I'm going to leave the plus 1 here. I'm not going to take 11 squared out, just 11. So that's going to give me 11 times 11 to the k plus 1. And I don't know for sure yet that that's useful. Maybe I'll take this one out and make it 121 times 11 to the k. I'm not sure yet, but I think because of this n plus 1, it might be useful to keep that there. Simplifying the brackets up here, we get 2k plus 2 minus 1 is 2k plus 1. And I'm going to do something similar here. Because there's a 2n minus 1 here, I think it will be useful to have a 2k minus 1 here. So to get a minus 1 where there's a plus 1, I'm going to take 12 squared in front as a slightly separate part to that term. I'll do that in a second. I'll finish off this line. So we've got minus f of k, so minus 11 to the k plus 1 minus 12 to the 2k minus 1 plus f of k. And I can see now that that was a good thing to do because this is the same sort of term as this, so I definitely do want to change this. So to do that, we've got 11 lots of this, and then I'm going to take the 12 squared out the front and do 144 lots of 12 to the 2k minus 1, because I've taken 2 out of that, minus 11 to the k plus 1, minus 12 to the 2k minus 1, plus f of k. Now I've got terms that are similar, so I can take 11 lots of this, minus 1 lot of this, that's 10 of these, plus 143 lots of 12 to the 2k minus 1, plus f of k. Now it might not seem obvious immediately what's going on here, you might have to ponder it over a little bit to see how this is helpful, but I've got 10 lots of this thing, which is part of the function, and then I've got loads of this thing, so I could take out 10 of these and separate them off to give me 10 lots of this thing, and then I've got 10 lots of the original function, evaluated at k. So we've got 10 lots of 11 to the k plus 1, and if I take off, or take out 10 of these, separate 10 of these from here, and that leaves me with 133 lots of these here, which is suddenly looking a lot more promising, plus f of k on the end. So I can see here now I've got 10 lots of the function. Let me make it really, really clear. I've got 10 lots of 11 to the k plus 1, plus 12 to the 2k minus 1, plus 133 lots of 12 to the 2k minus 1, plus f of k, and this is f of k. So I've got 10 lots of f of k, plus 1 f of k, that all becomes 11 lots of f of k, and I still have 133 lots of 12 to the 2k minus 1, and that has proven that f of k plus 1 is divisible by 133 if f of k is divisible by 133. So we get, therefore, true for n equals k plus 1, if true for n equals k. And that, together with the basis step, allows me to write the conclusion step, which I should write at the bottom, but I've run out of space. Therefore, true for all n as an element of the natural number set. And I hope that is enough for you to have a go at the questions from exercise 8b. And maybe I'll see you for recurrence relations in the next video.